day, I'm Dr. T and welcome to my dining room table. So today I would like to talk about chemical formulas. So I'm going to go ahead and I'm going to adjust my paper over this way, see if this looks a little bit better than the last video. So when we're dealing with chemical formulas, what we're looking at is how many of what type of atoms do we have in our compound. Now there's actually a couple different types of chemical formulas. The one I'm going to be looking at today is known as the empirical formula. This is going to be the smallest whole number ratio of atoms within my compound. This is typically used when we are dealing with ionic compounds. For molecular compounds, we typically use the molecular formula, which is the total number of atoms of each type in an individual molecule. However, ionic compounds, they don't have molecules. So, we're using the empirical formula. And it's actually a little bit easier to start with the empirical formula. You can work out a lot with those. Okay, so, making sure I can see you on the camera. So with the empirical formula, I'll start out with one of them. And let's go for the formula for red rust, Fe2O3. And a couple of things I can see from this. For starters, there's no punctuation separating the different symbols. This is why you have an uppercase letter followed by lowercase letters if there's a second letter in the symbol. Now, the next part is you'll see that there are subscript numbers. These numbers are telling me the ratio. This tells me that there are two, see if I can get my hand out of the way, there are 2 irons for every 3 oxygens. Remember when I discussed the atomic symbols and mentioned that lower right-hand corner? This is where we're doing that with, in the lower right-hand corner. Now, if that number happens to be 1, let's take another example like Na2O. Well, in that case, notice how the oxygen doesn't have a symbol. It doesn't have a symbol because it's implied. It wouldn't be there if it wasn't at least 1 oxygen, so we don't have to say that there's just 1 oxygen. You can also see that with CO2, quite a few other chemical formulas. We don't typically write ones. It's kind of like music. We don't put in redundant numbers. Okay, so now there's a couple other things that we can do a little bit differently. Let's say I take Na2CO3. In this case, this guy, let me grab a different colored pen. This guy is a polyatomic ion. Now, we're not actually marking that this is a, trying not to move the paper. We're not going to actually mark this as a polyatomic ion. You're going to expect the reader to know that that's a polyatomic ion. Ionic compounds can, just be forewarned, have more than one cation or more than one anion. So it can get a little bit interesting. So it's one of those you're just going to have to get used to what you're seeing. Most of the ones I'm going to throw at you will have 1 cation, 1 anion. Okay, so in this case, that's a polyatomic ion. There's no number after the polyatomic ion. So in that case, it's indicating that it's 1 carbonate, the CO3 is called carbonate, for every 2 sodiums. By the way, this is washing soda. It's used to make soap. Okay, so let's try this a little bit differently though. So let's say I have... Okay, so you'll have noticed an edit with a jump cut and a magically appearing post-it note. That's where I made a really embarrassing typo that I don't really want to put on the video. Okay, so let's jump in with me not looking like an idiot. So let's go for a compound, the one that's hidden underneath the post-it note. And this compound will be aluminum carbonate. Now, aluminum carbonate has a ratio of 2 aluminums to every 3 carbonates. So for the aluminum, that's pretty straightforward. I put a 2 there and we're good. But if I put a 3 back here, then there's a bit of an issue. Is that 3 carbonates or is that a carbon and 33 oxygens? Whew, that's a lot of oxygens. So to clarify, if we have to put a number down here, we stick the polyatomic ion in parentheses. We only do this with polyatomic ions, and we only do this if the coefficient for them is a number other than 1. So obviously if it's 1, we don't put the coefficient, there's no need for the parentheses. But if it's a number greater than 1, then we need the parentheses so we can sort out where that coefficient belongs to. Is it a part of the polyatomic ion or is it separate from the polyatomic ion? Okay, so now I've been pulling these out, and you've been like, okay, so he just has these memorized, and the answer is sort of. So let's actually look at how we figure out what these are. And I will go ahead and start with the iron oxide again. So let's pull up this iron oxide. Actually, I'm going to put the iron oxide and reserve that for later. Let's do the sodium oxide. So the sodium oxide, and you will see why I am reserving that for later here in a second. Let's go for the sodium oxide. So sodium oxide, I go to the periodic table, and I'm going to start looking at it. So on my periodic table, group 1, these typically form +1 cations. Group 2 typically forms +2 cations. Group 13 typically forms +3 cations. Notice how I skipped the middle. Notice how iron's in the middle. This is why we're skipping the iron oxide to start with. Transition metals do weird things. You need more information on the transition metals for the most part in order to know what's going on. Some of them are nice and predictable. Most of them are not. They can have more than one different charge. So for instance, iron exists in nature both as iron +3, which is what we have up here, and as iron +2. Copper exists as +2 and +1. And therefore, you actually have to know which one you're dealing with in order to do the formula. Okay, so for this column, 14, this is plus or minus 4. And truthfully, this is, we do not want to do ions column. Also, with this one, aluminum is the only one in 13 that actually behaves well. And carbon and silicon are the only, they don't behave well on a good day, but the only ones that really behave halfway decently. Next column for 15, this is going to be -3. So these form anions now. Notice how we're getting into the nonmetals. In this periodic table, nonmetals are this weird green, and then noble gases are this blue, and then everybody else is some flavor of metal. Okay, so group 16 is -2, group 17 is -1, and group 18 is noble gases. They like really do not want to form an ion or react with anything. They're very happy just being themselves. Okay, so now I can look at my sodium oxide, and I can actually tell my charge by looking at my periodic table. So I look over here, I see my sodium. My sodium is a group 1, so I can tell that sodium is +1. I look at my oxygen, it's a -2. So now I know the charges. For an ionic compound, the charges have to cancel each other. You don't get a net charge. Net charges are where you get lightning from. So what I need to do is figure out how to get these to cancel. And I can do that in a couple of ways. One, I can just kind of do some math. So I can just like, okay, what times 1 equals -2 times something else, kind of scenario. Or I should say, what times 1 plus -2 times something equals 0 is really what we're going for. So in that case, I could say, okay, let me grab another color pen. +1 times 2 plus -2 times 1 equals 0. Therefore, what I want is a 2 and a 1. And that works. And that's what I've got up here. I have a 2 here. I have an invisible 1 there. So I'm not going to write it. I accidentally made a spec, but I'm not going to write it. Okay, so yeah, now there is actually a shortcut. So I'll rewrite this to show you. -2, that's +1. I can take the number, not the charge, and I can do a crisscross. So I can take the 2 from the charge in the oxygen and put that on the sodium. I can take the 1 and put that down for the oxygen. Now, I do have to be slightly careful if I do that. So let's say I have something like, say, some magnesium sulfide. And I'll talk about naming in a separate video. So in this case, magnesium is over here. This is a +2. Sulfur is over here. This is a -1. Not -1. What am I talking about? -2. And so I can do the crisscross. And therefore I get the answer of Mg2 S2. Now, I ask you, is this the smallest whole number ratio? Nope. That's a ratio. It's a whole number ratio, but it could be smaller. So now what I need to do is convert this into Mg1S2, which is just written as MgS, magnesium sulfide. Okay, now let's go back to that iron and figure out what we are dealing with. So in this case, I have to give you one more piece of information because just from the periodic table, you can, where are you, buddy? You cannot tell what charge iron has because it can have two different charges. So I would have to tell you in advance that the charge on iron is +3. Okay, so now I can take the periodic table, I can look at it, go, okay, so I've got oxygen, that's -2, -2, I do the crisscross thing, and then that tells me, hey, I have iron 2O3. Iron oxide. Good work. Well, iron 3 oxide, I should say. Okay, so yeah, I've got this. It's going well. Let's take a look at the polyatomic ions. So let's go for some more aluminum over here. And I'm going to do, let's go aluminum nitrate. Now, polyatomic ions, you can either memorize these or you can rely on looking them up. Depends on your course setting. I'm not going to say in this video what my policies are because it does vary from class to class. I will post an announcement if you're in one of my classes as to which policy I'm doing for this particular class, or for your particular class, I should say. Okay, so aluminum. You grab that one, you go over, okay, here's aluminum, it's 3, so it's +3. So this is +3, then the nitrate, that is -1. And thus we do the crisscross. Yeah, that looks sloppy. So Al, that's a 1, so I don't do anything. Now the nitrate, there's 3 of them. So I'll do open parentheses, I'll put the nitrate, and then I will close parentheses, and I will put a 3 there as well. Yay! So we have aluminum nitrate. Fairly straightforward in doing this. This is one of those areas where practice makes perfect, so I encourage you to practice a few of these. It's pretty easy once you get the hang of it, but it's a little bit awkward when you're doing it. Major caveats, once again, knowing this, bump all my papers, knowing this pattern is incredibly helpful for you. Second caveat is do check to make sure you don't run into a situation like this, where you have a smaller ratio that you could possibly have. Typically, you are going to run into it, the 2s and 2s. So picking one from this column and one from this column is kind of the common way. There are other pairings which can get you into trouble like that, especially with certain polyatomic ions. So just double check. So as soon as you do it, just do one quick check. Is like, is this really the smallest whole number ratio? If the answer is no, well, fix it. Okay, quick aside, when we're talking about the charges, a little bit more explanation as to what's going on with these guys. So when I look at them, you'll notice the pattern of 1, 2, 3. Now, think back to valence shells. Let's look at why. How many electrons are there in group 1's valence shell? If you said 1, you're correct. If you're going, wait, that's the same charge, you're also correct. For groups 1, 2, as well as for aluminum, really what they're doing is they're shedding their valence shell. They're trying to get down to the next one below it. It does take energy to do so, but shedding their valence shell is pretty low energy, and the energy they get from forming a lattice is more than enough to overcome the tiny amount of energy it takes to shed off those electrons. Now, for these guys, these have shells that are partially full. So if you think about how many electrons are in their valence shell, and then think about how many electrons could go in the s and p orbitals together. So your valence shell is typically going to be your s and p orbitals. 3 p orbitals holds a total of 6 electrons, plus an s orbital holds 2 more. That gives you a total of 8. This is sometimes referred to as the octet rule. I don't particularly like using octet rule because I like to zoom in and talk about the actual orbitals. because where it's from, because when you get things where the octet rule is violated, well, it's not violated, it doesn't exist. It's the orbitals are doing their thing, and you've got situations where orbitals do their own thing. So in this case, these orbitals are one electron from being filled. The s and the 2, or the s and 3p's are one electron away from being filled, and thus, getting noble gas configuration. You'll get a little bit of energy if you can get that electron on there, and thus they will try and form an anion. Likewise, these guys, 2 more electrons, you can get some energy out by putting some electrons on there, and then this guy kind of 3. Carbonate silicon, it is generally much more favorable from an energies perspective for them to be sharing electrons than forming bonds. So in theory, they could gather up more electrons and fill an octet. They could shed off their entire valence shell, but in reality, they don't like it. So you rarely see those, and when you do, they are incredibly unstable. But yeah, the reason these numbers exist, I'm trying not to move the paper, the reason these numbers exist is this is the relationship between their valence shell and their orbitals, and what those orbitals will be interested in doing. The anions are all very electronegative. They have a very strong pull on their valence shell. The cations are all very low electronegativity. They have much weaker pulls, and thus it's much easier to shed their valence shell. So yeah, with that said, have a wonderful day, and I'll see you in later videos.